Okay, so today we're going to start talking about waves. And to really understand waves, we need to understand oscillations. Now, an oscillation, usually in physics, is something that fits into a category of moving back and forth. And we're going to talk about a very specific back and forth movement today called simple harmonic motion. Before we get started, I want to show you what your homework is so you can be on the lookout for how to answer these questions. The first question is, what is the only thing that affects the period of a pendulum on Earth? Number 2, draw a sine wave. Where do you see this pattern in nature? This will tap into your math background a little bit. And 3, if you want to make a pendulum on Earth with a period of 1 second, what length must the pendulum have? So, to get started, let's talk about an object vibrating back and forth because it's attached to a spring. So, if an object vibrates back and forth, and it takes the same amount of time to go back and forth every time, it's called periodic. So, if my box right here starts at x equals 0, that means the displacement is 0 at that point. That's its happy place. And I displace it, I pull it all the way over to the side so it looks like picture number 2. The spring is then really stretched out, and the spring is going to want to pull it back this way. Apply that force to it. When that happens, if you just let it go, that box is going to move this way and then back, and then this way and then back. And it should take the same amount of time to go left as it does right. That is periodic motion. Now, we've already kind of talked about a mass attached to a spring. Hopefully you remember way back in the beginning of the year, we talked about Hooke's law. Remember, force on a spring is equal to the spring constant times displacement. And you did a lab to figure this out. You took a spring and you attached weights to it, and you measured how displaced that spring got. And when you put it into Logger Pro, you found that the force of gravity acting on that specific mass was proportional to how far the spring stretched. And it stretched from an equilibrium position. And this is a really important point. So if we go back to this picture here, our equilibrium position is the spring's happy place. It's that x equals 0 right here. At this point, the spring is not stretched or compressed, so the box will just sit there. It won't move. In order to get it to oscillate, we have to physically move the box from this position by either stretching or compressing the spring. So this is what we mean by equilibrium, the spring's happy place. Now, a few notes about this that we should already know, but a little refresher. The minus sign in our Hooke's law equation, remember it's F equals minus kx, the minus sign indicates that this is a restoring force. So what does that mean? Well, if I have my spring all stretched out, my box is way over here, I have pulled my box this way, but the force wants to bring it back this way. It's a restoring force. So it always acts opposite of the displacement. If the box is moved, if this is x equals 0 right here, if the box is moved to the right of that, the force will be to the left to pull it back. If the box is moved to the left of that, the force is going to be pulling it or pushing it back the other way. So the force and the displacement are always opposite each other, which is why there's a negative sign in this equation. K is the spring constant. K tells you how springy something is. So it is the springiness. The more springy your spring, the higher the spring constant. So if you have a slinky that's really easy to pull apart and stretch out, that has a really low spring constant. If you were to take a shock out of a car, that is really, really, really hard to stretch out, so that has a very high spring constant. Now, the force on this object is going to change over time. If you pull the object really far back and really stretch that spring out, there's going to be a large restoring force on it. If you only pull it back a teeny, teeny, tiny bit, when you let go, the force is going to be very small. So, The acceleration of this box is not constant either. Sometimes it will be moving quickly and slowing down. Sometimes it will be moving slowly and speeding up. Sometimes it won't be accelerating at all. It is not constant, it changes. So let's talk about the oscillation of this thing and learn a few key terms. You've probably seen these before this year, but we're going to go over them again. The first term is displacement. Displacement is how far the box moves from equilibrium. So if this is equilibrium right here, and we move the box over to this point, this distance right here is the displacement. How far that box was displaced from equilibrium, or from its happy point. The amplitude is the maximum displacement. So if we start at equilibrium, and we pull that box out to here, and that's as far out as it goes, that is going to be our amplitude. If after that the box comes any farther in, let's say it only comes to about here, that is no longer the amplitude, because the amplitude is the maximum displacement that you can have. Anything in between is not amplitude. One cycle is a full to and fro. That means if we have our compressed box, it needs to go all the way out, stop, and come all the way back. This is one cycle. If we were just to watch the box go out and stop, that's half a cycle. If we watch the box go out and back and then out and back again, that's 2 cycles. So it is a full all the way there and all the way back. The period is how much time it takes to do this one cycle. So if this box can go there and back in 2 seconds, that is the period. The period is 2 seconds. And we already talked about frequency a little bit. Frequency is the number of cycles you complete in 1 second. So if it takes 2 seconds to go there and back, it's going to take half of a second, or half of a cycle in 1 second. So remember that the period of anything is equal to 1 over the frequency. So if you have a period of 3 seconds, that means you are going to complete a third of a cycle for every 1 second. And that's your frequency. Now, any vibrating system where the restoring force is proportional to the negative of the displacement, like Hooke's law, F equals negative kx, force is proportional to the negative of the displacement. This is called simple harmonic motion. And I'm going to abbreviate that SHM because it's much easier. And this object is usually called a simple harmonic oscillator, and it moves in a very specific way. And it turns out when you have a simple harmonic oscillator, you can use special equations to solve for the period, or how long it will take that object to make 1 cycle. So if we have a spring system, let's say that it's hanging instead, and this is its happy place right here. This is equilibrium, x equals 0. Our spring has some amount of mass on it, and the spring itself has some spring constant. Now, if I were to pull this spring down, or pull the mass down, the spring would want to pull it back up. So when I let go of it, it would bob up and down in simple harmonic motion. If I wanted to figure out how long the period was for this, I could set it up experimentally and time it, or I can use this equation. Period is equal to 2 pi times the square root of the mass over the spring constant. Now you might be looking at this saying, what the heck is going on? Because this is a crazy looking equation. It all comes down to sine waves. So hopefully you've all seen a sine function before. It looks like this. It goes up and then down, and up and then down, and up. And the maximum, if you just have sine, is 1, and the minimum is -1. And the equilibrium is at 0. All simple harmonic oscillators follow this pattern. So if I were to set up a mass on a spring, like in this picture, and I were to let it bob back and forth, and as it was bobbing, it let sand out the bottom of the mass, you would leave a trail of sand that looks just like a sine wave. This is exactly what pattern it traces. And it's the math surrounding this is why this equation looks so weird. So when we have a mass on a spring, we can calculate the period knowing only how big the mass is and how strong your spring is, or what the spring constant is. Now, it's kind of interesting because we can plot displacement, or how far we move that object from equilibrium, through a sine wave, just like in this picture. This top graph right here shows us displacement, or where the object was at a given time. But from that, we can also figure out how fast it was moving at a given time and its acceleration. So if we think about this for a second, this mass is going to move back and forth. At this point, it's trucking. It's moving very fast. It's being pushed out past its equilibrium point and then going out to its farthest amplitude out. So this is where velocity is a maximum. It's very high in the middle. And on the ends, right here and right here, this is where velocity is going to be at a minimum. It's going to basically come to zero so that this object can change direction. Now, if we look at these two graphs, we can actually see that happen. So this graph is of displacement, and this graph is of velocity. And if I were to draw a straight line from where the displacement is at equilibrium, I would see velocity is at a maximum. It is the farthest away from that zero line as it can be. Because when your spring is moving through the equilibrium point, it's traveling the fastest. Now, when the object is physically as far out as it can be, and the spring is completely stretched or completely compressed, it needs to change direction. And in order to change direction, the velocity has to be zero. So it's kind of interesting. You can basically take the same graph for displacement and velocity and just shift one over, and it will be the same thing. Same thing happens for acceleration. Where your object is slowing down and changing direction when the spring is very stretched or very compressed, that's where the most acceleration happens, because it's changing direction. When your object is moving as fast as it can right through the equilibrium point, it's just going to keep on going in one direction. So at that point, the acceleration is basically zero. It's traveling at a constant speed right through that equilibrium point. Once it passes that point, the speed is going to change a little bit, and that is where the acceleration comes in. But at that point, when it's crossing the equilibrium, the acceleration is zero. For those calculus buffs out there, these are derivatives. So if you're given a graph for the displacement of your object, you take the derivative of that to find its velocity. If you're given the velocity of the object, you take the derivative of that to find acceleration. And that's where these graphs come from. Now, we know that a mass on a spring is a simple harmonic oscillator, but we have another example that we see in everyday life, which is a pendulum. And a pendulum is a mass at the end of a lightweight cord. We assume that the cord does not stretch and that its mass is basically zero. It's a very, very light thread. And we have a mass on the end of it. And if we displace that mass a little bit, gravity is going to want to pull it back down to Earth, and it will end up swinging in simple harmonic motion. Now, remember, in order for it to be simple harmonic motion, the force must be proportional to the negative of the displacement. So if we look at this picture, we have our string right here with our mass on it, and it is displaced this far from equilibrium. That distance right there is equal to mg sine theta. It's all about trig. So mg is weight, the weight of this mass at the end of the pendulum, and sine theta is the portion of this triangle that is in the x direction, the one that's lined up with this line right here. So it is true that the force is proportional to the inverse of the displacement. And we, just like with a spring and a mass, can calculate the period of this pendulum by using a special equation. And that equation is the period is equal to 2 pi times the square root of the length of the string divided by gravity, which you all know here on Earth is 9.8 meters per second squared. The really crazy thing about pendulums is that the period does not depend on the mass. So if you have a 4-foot string and you put a 1-pound ball on the end and you displace it a certain amount and let it go, it will have the same period as if you take that same 4-foot string and you put a 100-pound mass on the end and displace it the same amount. The only thing that will affect the period of a pendulum is the length of the string. So if I have a little baby string like this, this pendulum is going to have a short period because it doesn't have very far distance to move between its amplitudes. If I have a really long pendulum, this one can move much, much farther. Its amplitude is a greater displacement away from equilibrium, so this period will be much larger. So, given that information, answer these 3 questions and come in with questions the next time I see you and be ready to hand these in.